Frank Hughes has worked extensively in spaceflight training, leading the establishment of operations and training process for Space Shuttle and Space Station. Frank tonight will review the history and evolution of training over the course of the evening. He'll highlight the challenges of implementing a successful training program for future space missions that must accomplish working with the ultimate system, the human element. With that, Frank.
Thanks very much. Really nice for the opportunity to come and speak to you all. What I want to do is have some fun with this. First of all, it's a learning experience, so I'm going to entertain questions. I'm going to try something a little different. It's a nice sized crowd. I'm going to do these kind of by phases, and so at the end of each phase, when you see, did we learn anything, that's the chance when you can try to learn even a little more, okay, by asking questions. Okay. The fact is that I personally joined NASA in 1966, May of '66. So my experience base extends none of Mercury, okay, and the first 2/3 of Gemini was all done by the time I walked in the door. So I was there for 9, 10, 11, and 12, and then coming down through the years. What I'm going to do is run slides here. The show is over there, so you can just hear the voice. I'm going to try to, I don't have a pointer here, so what we're going to do is try to mouse it around when we're going through some of this stuff. But the big thing is that I want to tell you a story. I'm going to get my finger on the button and we'll do the thing here. Oh, goodness. That's even better. Thank you, sir. Okay, we'll run a test here. Okay. Ooh, that's a nice color. I like that. Okay. Let me take you back. We're going to give you an idea. In 1958, President Eisenhower signed the National Space Act. The year before, of course, we had Sputnik. It was a big surprise to everybody. In fact, before they got even into the surprise, they got a second surprise because in October they launched a satellite, the Russians did, and in November, even Big Bear, a much bigger satellite. And so it just blew us away. All right. In 1958, we formed NASA out of all of these pieces. The original NACA, which is the National Advisory Committee on Aeronautics, then the Army, Navy, Air Force, even the Coast Guard had a piece of the action on this early days. The thing is that when you start talking about my part of this deal, which is training, I want to give you a definition, just so we're all in the same place. It's some kind of an activity that leads you to an skilled behavior, okay? And say it another way, it's the acquisition of knowledge, skills, and competencies, okay? Now, you've all done that. You've been to a place, you've been forced to sit in a place just like this, like tonight. And you know that some of those experiences are good and some okay. But the fact is that you've got to go through it. When the National Space Act passed and NASA was formed up, we didn't know any of this stuff. We did not know the skills that would be needed to fly in space. We didn't know the knowledges. We didn't know the attitudes. Attitudes are the competencies that are going to go on. Okay, so it was tough. It was a really dynamic situation. So the first thing out of the barrel, they created something called Mercury. Okay, we're going to go by programs here. Initiated in 1958. Almost immediately, they went out and hired a bunch of astronauts. You know the original 7 astronauts and all that sort of thing. Okay. They started in 58, they completed in 63. During that time, first time in space, they wanted to do 3 things. Orbit somebody, successfully got them back. Okay. Investigate their ability to function. Now, a lot of people think you couldn't swallow. You couldn't eat. Okay. Your blood wouldn't pump. All kinds of things. There's a lot of stuff. And then recover the person and the spacecraft successfully. Okay. Well, this was the Mercury ship. Now it had a escape tower on the top of it, but after a couple of minutes on flight, those jettisoned, and this piece gets to orbit, okay? When you do, this is a very, very, very simple spacecraft. This is the main instrument panel, okay? You had only about 50 switches and controls. It's very, very simple. Come on in, guys. 50 switches and controls, no onboard computer. No onboard computer at all. They had rate gyros that if you took the stick and stirred it around, you could change it. You could have rotate the spacecraft, but you could not translate it. You couldn't make it move, change orbit, do anything like that, except to retrofire. You had 3 solid rocket boosters that you had to, when you triggered them, you better be pointed in the right direction. So you're going to go somewhere, and if you want to go home, you have to be pointed exactly right. It was so elemental that you had lines on the window for retrofire. You would turn around and you look at the Earth, and if the Earth was going away from you, then you were facing backwards. You put this line on the window and fire the rockets. Okay? The whole trick was to compute when to fire. Okay, so you get into the target. And so in the control center, there was somebody called retrofire officer, and that was their only job. Always compute the things to get the crew down into someplace near where the Navy had ships. Okay? Now, just some pictures. This was the Mercury procedures trainer. It wasn't even a simulator. The host computers were analog computers. 3/4 of the room doesn't even know what an analog computer is. But the fact is that it just did circuit boards that changed voltages and divided voltages and did all kinds of things and ran all the displays for the crew. You had to climb into it like this. Okay, in fact, this is, you can see the kind of thing when you get in. And then on the real vehicle, there was a periscope that lets you look out. Okay, and so this is a very elemental kind of thing that would give you kind of a horizon, to let you know there's something out there. It got better over the years in the training, but it was the first visual system, if you will, for this, but very, very simple. Okay, and you can see inside, they were sitting at this thing. It's as good as it could. They could get in with a suit. There was a certain system, so you just had cool air flow through it. And then you would be able, this is Scott Carpenter working through this kind of thing. However, it was good enough. We launched 2 of these Redstone rockets, carrying people suborbitally, and then 4 manned Mercury Atlas rockets. The longest one, the 4th flight, was 23 hours in space. Okay? John Glenn only went around Earth once, came back to it. The other guys, bigger and bigger times, 3 orbits, 6 orbits, and then 23 hours. It's interesting that Gordon Cooper, who did that one, had a terrible failure in his environmental control system as soon as he left it off. He was roasting in his space of the entire town, but he wouldn't tell anybody. Okay, that is, because they knew they'd bring him down as soon as he. So he stayed the entire flight, did everything he was going to do. When they got him on the ship after they landed in the water successfully, got him up, he had sweat inside of his spacesuit up to the middle of his thighs. He had sweated out that much thing, and that's the kind of stick-to-itiveness, I guess you'd call it. We had a control center that was, by the way, the simulator. There were 2 simulators. One was in Mercury, was built by McDonnell Douglas. So the one trainer, I should call it, was in St. Louis, and the other one was at MCC Cape. That is, the mission control then was at the Space Center down in Florida. Okay, and so at that time, what we learned here is how to operate, how to run a control center, how the philosophy is set up, and all that kind of thing. And it worked out quite well. It was interesting because the network is such. First of all, you don't need, you think about all this constant contact now, but the fact was that all of these circles, that's the only time you could talk to people. Okay, there was a place in Guaymas, Mexico. There was a station there. The spacecraft would come over the horizon. You could talk to them as long as they could, and then they'd be gone. 2-3 minutes max. That was it. Okay, and so all the rest of the time, the crew is on their own. Okay, and that's just how the life was. So, what did we learn? First of all, people can survive. They can live and work. Simulators, trainers, are realistic, and you can learn enough about the spacecraft that you can do some good things and be prepared. We also found out that crew can see and acquire photographic data and all other kinds of data from orbit. And for one of the bad flights that we flew, one almost messed up, is watch out for your fuel, your maneuvering fuel, and save it because it's your life depends on it. Okay, this is one of the first things. So now as a training cadre, we're going to start watching for fuel. Okay? Always make sure that the crew is thinking about this. What was about is Scott Carpenter, when he flew, he was kind of an experimentalist, and he had a lot of fun. He was looking at the Earth, and he was flying around looking all over and all stuff. And he almost used up all of his maneuvering fuel, which of course is the only thing he could use to hold attitude for that retro maneuver. Okay? but he made it. But he also fired late. In the training somehow, he didn't understand that the speed you're moving, if you fire 15 or 20 seconds later than the people on the ground told you, at 5 miles a second, you're going to be way the hell down the field, okay? And he landed at the, what we call the toe of the footprint, okay? That is, it's lucky that there was a destroyer way positioned way down at that end. Otherwise, it would take 2 days to get to him or something. Okay, now, Gemini. Oh, that was when the questions went by. Okay, let's keep going. The goals in this one now, Gemini was really quick, okay, is that you're going to subject man and machine to spaceflight up to 2 weeks duration. Now that's pretty spiffy. We just flew, somebody that 23 hours was a big deal, or even one hour and a half, but now we're up to 2 weeks. Rendezvous. Rendezvous was a big, scary thing we're going to get into. So rendezvous and docking with vehicles up there. Maneuver, station keeping, flying in formation like with airplanes. And then to perfect methods to make sure that you could not only just enter the atmosphere successfully, but pinpoint landing, that you could come down just where you want to land. It was a 2-person spacecraft, flew missions between, 10 missions between 65 and 66, a digital computer on board. This is a massive change. It had 4K of memory, okay? And that could compute and display rendezvous solutions to you. It was really quite good. It had a stabilization control system with rate gyros, kind of like the first one, but better. But it could translate. Okay, now you had a set of jets that you could physically change the orbit. Okay, you could maneuver and do the thing. And of course, this is what you use now to red fire and come home as well. There's still some solid motors for that. You had an environmental control system good for up to 14 days, and the fuel cells, instead of the batteries and mercury, you had fuel cells, okay, which was a big deal. And this one was about 200 switches and controls, okay? More complicated, you can see. The 2-person spacecraft, it's like a 2-person airplane cockpit. This is again built by McDonnell, and this is what it looked like, okay? There were 2 of these simulators, one in Florida and one in Houston, because Houston was just coming to life. Okay? It was being built in Building 5. The first simulator that ever came into Building 5 on site was GMS, the Gemini Mission Simulator. Okay? When you were able to get in there, this is the one in Florida. You can see John Young and Gus Grissom. And this was a great simulator, a step upward, if you will. And you'd have to call simulator. This is Wally Schirra and Tom Stafford working on their flight. Okay? You can tell Stafford because of the shine. But we went through these things, and it was a marvelous thing. It was just a lot of fun to work with Mercury and in Gemini. What turned out to be something else. In Gemini, we also started working about EVA. That is, we had to do a couple of things. We were going to rendezvous dock with these satellites that we call the GINA, and then you would EVA. You'd go outside, you would go across and hook a tether to the other vehicle. Then you undock and move back, because we wanted to see if we could save fuel by running these 100-foot tethers out there. Okay. And as it turned out, the rendezvous was pretty good relative to the other things. This is another picture of a different simulator. How many of you have been in Building 5? I want to talk about just people that you know what's going on, and then some others. What is now the space station training device was a big motion-based simulator, okay, where the Agena would move up and down the whole length of the thing and go up and down, or left and right. And the Gemini was just static on one end. It would move back and forth. So it was a docking simulator, okay? So you practiced, and it was all black. It was painted all black in there. And then you get into this thing and rendezvous and dock. And we'd have the lighting, so it looked pretty good. That was called a translation and docking simulator. We also, through the things on this one, we learned about EVA. We had 3 bad EVA situations. The people got out, they didn't have enough handholds, they didn't have a good place to anchor their body, and so they got all sweaty and tired out because they were just working too hard. The very last flight, the training got better. We used zero-G airplane flights. This is Bill Anders working on one, and Buzz Aldrin went through a bunch of things in water tanks and everything, and we got it off. When we finally came to fly, this is the Gemini Titan. We wound up rendezvousing the first time on Gemini 6-7, And the reason it became 6, 7, 6 was supposed to be the first one to do a rendezvous, but its Agena blew up on the way to orbit, so they never launched. And then 2 months later, 7 was supposed to go up for a 14-day flight, so they literally launched that one, turned the pad around within a few days, and then launched 6. And so they actually rendezvoused. They couldn't ever dock or anything, but the two Geminis looked at each other, took pictures, made fun of each other, and put beat Army up in one and beat Navy, and you know. It was kind of interesting. Let's see. I'll make sure I cover all these things. I think that the tethers was probably the most interesting thing when you got going. This is the. Don't go too far. That's what the Agena looked like. It was actually an Air Force thing, but over time then we docked with it on 10 and 11, put out these tethers, and then we were trying to do gravity stabilization. It weighed more than the Gemini did, so we'd fix it so it was below them, and they'd do a gravity gradient. Gravity was pulling on the Agena just a little bit more, so you would actually go to an orbit with the tether vertical. Okay. Well, that's part of what we're talking about with the space elevator. Okay. We explored it some with the Italians in the late 80s with this kind of thing. We did some with the shuttle, but the dynamics is really awesome, and we have a lot of work to do. The control center in Houston was finally came online, okay? And this is the familiar pictures you see down there. Gemini 3 was the first one where they were operating and watching what was going on, and they flew in parallel with the control center that was in Houston. And in Gemini 4, the Houston MCC became the prime, and then we decommissioned the one in Florida. And then, in fact, lately, apparently they just knocked it down. You know, the building hadn't been maintained, and then they just destroyed it. So, the extra things here, you don't see all this stuff. Those were big XY plotters for the rendezvous. I mean, we were so worried about rendezvous. We had all these extra procedural things going on. And the concern was that you could be able to see in detail what was happening, and you could give the crew some help. As it turned out, we were able to move through this thing and do it really, really well. We learned that rendezvous was relatively easy, done properly. I mean, you could screw it up. But the fact is it was not the bugaboo that people, once you understood the math, the execution was not bad. So that the procedures were developed, and then the training got better. Okay, you understood what you were going on. Docking and station keeping was relatively easy the same way. Once you understood the physics of what was going on. Saving fuel got even more important, and of course it continues to be a lifesaver even today. You could find out people could live and work in space up to 14 days. But the crew that did it will say that after living 14 days with him in the front seat of a Volkswagen, it's not something they want to do again. This is the worst situation you might think about. EVA was a complicated. We had our disappointments with it, but as it turns out, it got with better planning, better equipment, and better training, it made it easy. And the tethered operations, okay, the big thing would save fuel and so on. So that was a major, major change to what was going on. Okay, now Apollo came along, almost butted up against that thing. So the goals here went way beyond. We're going to land on the moon, men on the moon. I want to show that later. Our goals were that we were going to go back to the moon. We weren't just going to land. We had an exploration program going. We were going to establish the technology that we used to meet other national interests, our military interests, and so on. We were going to achieve preeminence. Okay. We were going to carry out a program of scientific exploration, and we're going to develop capability to work in the lunar environment. And we were working hard on that. The systems were fascinating, okay? Compared to where we were, now you got two vehicles, the command service module, and it's called that because there was a command module and a service module separately, glued together for most of the flight until you're ready to do reentry. And then a lunar module. We did 11 manned flights between 68 and 72. Now, the same digital computer was used in each machine, different software, but the same one. Now, how many of you have Delco spark plugs in your car? Well, then Delco built the simulator computers. I mean, built the spacecraft computers. Okay? They got the contract. GM, in other words, was the one who built those. That machine was 36K of memory. 36K. Now, a cheap wristwatch has more than 36K. But that's what it was. Of that, by the way, 2 were erasable, what we call RAM today. And the other 34 was like a PROM. It was hand wired into it. So it couldn't be armed with a hammer. I mean, you couldn't hurt it at all. Environmental system was great, much more sophisticated. There were 3 good fuel cells. The RCS, on this case now, before we'd used hydrogen peroxide kind of reaction jets, and now we're using hypergolics, okay? And we've done that since everything we've flown, we've used hypergolics in it. Big engine, 21,000-pound thrust on the CSM to help you get into orbit around the moon and then later out of orbit. The engines on the LEM, ascent-descent stage, the descent stage was incredible because it was throttleable. You had to throttle it. We'll talk about that. You had to learn how to fly this thing down to the ground with one hand on your attitude and one on the throttle. And the thing about 350 switches in the command modules, about 200 in the lunar module. So you can see the systems are getting up, more sophisticated, going up, and so on. We've got one of our LEM guys over here, Jack Knight, who was sitting in through all these things. He'd be grinning at me as I talk to you this thing. Look at the size compared to what we had in Mercury, Gemini, Apollo. These are the relative size of those spacecraft, but look what you did here. Okay, things are coming up a lot. Okay, a lot of changes. The command module main panels will look like this. You had a couple now really good attitude indicators. This is called the DISCI, the display keyboard, and so on. Okay, and then the LEM. We're not going to try to get into the details. That's another lecture if you want to talk Apollo to details. But these are the windows you always see in the LEM. You had controls. This is the hand controllers for the commander, and then over here, a complete set for the pilot. None of the pilots got to land on the moon. Everything worked like a charm. There was no seats. You stood on the LEM, and in fact, you had some harnesses that held you to the floor. Okay, it was kind of like an upside-down parachute device where you had a connectors that you held it down, bouncing around. But weight-wise, we couldn't care to take seats. We were getting more sophisticated. There was lectures, just like a lecture room. This is a guidance navigation thing from MIT. And in fact, this is one of the navigation platforms. This is an inertial measurement unit. This is some of the actual training material at that time. So you can see that they were learning what's going on, the steps along the way, and so on, and how the procedures are going to have to work. This is one for entry. So these are actually from some of our training material that we had at the time. We had a lot of simulators. We actually had a mission simulator for the command module and another one from the LEM. Okay, this is a picture taken down in Florida, which is at the time where I was working. This is a command module simulator. The brown is command module and the green is LEM. So this is actually taken from one of the command module simulators, looking down the hallway as you go through. This is the instructor station on each of these. You can see one over here. You can't see the one for this, the one we're standing on. When Gus Grissom saw this the first day, he called it the train wreck. You can see how it might be. The reason I have the strange things is it's a visual system for each of the windows. And it was a combination of video and movies and star simulation. And they're all combined with beam splitters and so on to give you one image coming through the window. Okay? And so that's what all that was about. And that's a whole other lecture you can have about visual system. Here's Frank Borman, Bill Anders getting in the simulator down in Florida. And inside, it was a hi-fi simulator. That is, it was as good as you could make. This is the instructor station. And you go through this. The crews, in training, it's an interesting place. If you're training people, it's not on public display. You can be your real self. You don't have to sign autographs, okay, all this sort of thing. The things that you do, you go up and screw up. Nobody talks about it out of work. You just fix it. This is what it's about. And so they were very relaxed in all of their training, as they are today. Okay. This is the computers now. The host computers were from a long gone computer called Computer Corporation of America, and that was a DDP-224. Incredibly power machine. It had about 350K of memory at the time. And it took 4 of them to run the simulator. One did the visual, and the other 3 did the equation motions and all that sort of thing. Remember that worry we had about rendezvous and everything? Big XY plotters just to make sure that we could do it right. And you can imagine the instructors that we had by this time. Wish I had some of those narrow ties now. See, I can maybe do something. This is the interior of that spacecraft. You can see that you could do complete missions, you could do launch, you could do orbit, rendezvous, travel to the moon, and so on, all the things that you had to do. And then finally entry. And you could work in short slave, which mostly did, or you do it in SpaceX. John Young there in Apollo 10, that's his position then. We also had in Building 5 something called a Dynamic Crew Procedure Simulator, DCPS. It would actually load 3 people in, and it would tumble you, okay? You would go through the things, because if you have that escape tower like we did on Apollo and on Mercury, and you fire it, the dynamics are awesome, okay? Really tough on you. And in fact, by getting rid of all that stuff is why we got to an old lady's ride like the shuttle is, okay, where you never see more than 3 Gs. This thing, it would not put the Gs on you, but it would give it the tumbling and all the kind of things that would go on for this kind of situation. It also had stars out there, so out the window you would see how tumbling you are, as if you could with your inner ear telling you what was going on. We had the Building 29, but it still had a centrifuge, okay, which has been decommissioned. This is the gondola where you would put 3 people in, and you could run an entry simulation, or you could run a launch simulation. So they'd go through the Gs, okay. A bad abort going uphill with one of those abort towers, like we've chosen to go back to, and I'm not going to get into the politics of that one, but somebody said that was reducing risk. Somebody never rode one of those, I tell you. In a bad one, you can get 16 Gs. Okay? And it's because you come off this thing, you're not going very fast yet, and now you'll just fall straight in. It's not long. It's a hell of a peak load, but it is really bad. And that's why we had a gondola centrifuge, because people could not stand that kind of thing. Okay? So when you go back to the thing we built, it means that just the average bear that used to be an MS kind of candidate probably can't go. Now, going back, that was the command module kind of stuff. Now I talked about the LEM. Just to give you a little bit of idea of how this worked, when you're ready to landing, the CSM stayed in orbit, but the command module, the LEM, on the way down, at 50K, you start the engines up and you fire into the direction you're going. So my hands are going like this, in the direction you're going. When you go on down, as you slow down, you have to tilt over some to control your descent rate too, until finally you're hovering, then you touch down. But along the way, we gave all those things names because the software would change what it was doing, and you, of course, as the pilot, would change what you did. Generally, we came down on automatic on all of them until you got the low gate, and the crew would turn over. By then, generally, they could see the place they're going. Okay? And then you get into this landing phase. When you get through this braking phase, your thrust is about 6,000 pounds up here, and you can see it's throttled down to 2,800, and then down and down until whatever it is. So you get in vertical velocity is all you got. You've killed all of the horizontal velocity. Now we did this before we had the other simulators. Langley had built a huge, big landing simulator like this that actually was outdoors. It flew along, and you'd come down. It's like a big crane. There's big rails on each side, and you could land like that. When we got to the mission simulator, it supplanted that one pretty good. We went to the digital phase. And what you got into is you'd get into this simulator. This was the crew station now. So it was, again, high fidelity digital simulations of what's going on. And here's Pete Conrad and Al Bean. And they could do everything you needed to do in there except sleep. That is, we didn't have the sleep stations and all that stuff. But you could go in there and you'd run an entire simulation. And on top of that, we could run this with Houston. There's a whole set of things we have to do as train, not just the astronauts by themselves or the flight controllers by themselves. We had to work them together. I want to talk about that later. This is just another fisheye view of that whole area. Now, when you got into this, the simulator, we were just looking here where the crew is. This is called an LNA, a landing and ascent thing. And basically, there was a plaster Paris, or it's actually a plastic model of the exact place where you're going to land, okay? And underneath it was a huge XY plotter that had a camera sitting up looking this way. And so it moved back and forth in XY as where you're positioned. And the surface of the moon would come down. This thing had magnification, and it had a little prism that moved when the spacecraft turned. So you would look out the window and you'd see where you were going. And then the reason we hung the LNA upside down is the magnification was so much that dust would look like boulders. So we had to do it. Well, of course, we were young. We were young. And so a lot of things got stuck to that surface. There was just a time where Scotch invented magic tape. So you couldn't see the tape we used. So we'd go out, catch one of those big palmetto bogs, they call it. It's a roach in anybody's language, and it's about 4 inches long. And we'd not kill it, we'd tape it alive to the thing, just near where they're going to land. So the first one in the morning, they come in and they put in gear and they do, and I'll be real professional. They come flying down and touch down and look out the window, and there's this thing. The antennas waving. All it's trying to do is get loose, you know. Pharrell Shepherd, one day landed, and there's a little 6, you know, like a golf flag hanging, you know, in one of the craters, like it's a golf hole. You know. Some days when we do these things, you would land, you could fly to the moon in the command module simulator. Then you get out, separate, walk into this one. You go through the procedures and land. Then you get out and go further down, about another 100 feet down through the building, and you would get to this area where there was a mock-up of the lunar module. Okay, and we did this a lot. So that when you get here, you'd carry the flag out. I mean, you did the procedures. You went through the whole steps. Of course, we're inside the building because this is Florida. It rains like hell periodically, you know. So, but we'd set up all the things. The Apollo 12, they were going after a surveyor. This thing on this slope. This is the actual slope it was on. It's about 12 to 18 degrees, and we'd go over there and rendezvous close enough that we could go over near it. And then we actually cut off pieces of the simulator and bring it back, of the spacecraft, and bring it back. Okay. The idea being that it had actually been inoculated with germs. People wanted to see if we could get it back, how those organisms had survived in space with the radiation. Kind of scary, the fact that they were just fine. Man, they were happy as little clams. As soon as you give them a little water and a little warmth, they're up and going again. So it's an interesting thing. Then you would leave the building on a big sim. You would have one of these things. It's a trainer, a roving trainer, and you would go outside. Now this is Florida. You can see the building where we started from is over here. So now you're out in these palmetto flats running around through the weeds, and you would go out, people would be ready, and they'd have simulated rocks, and you'd stop and do your thing. This is the best you could do. But then get out, and it's funny. We take pictures of these guys in these spacesuits, and they're steaming and, you know, going on. It was really great. John Young and Charlie Duke left the room. They were not always with people because you'd go down a road and then there'd be some more, you know, something else to do in another place because you'd simulate how far you had to drive around through the woods. Well, I had to stop and I said, Houston, you know, this is Apollo 16, whatever they call themselves when they're on the surface. And he says, send the parks and wildlife people out here. And of course the captain said, say again, John. They said, send them. Turns out they had encountered about a 12-foot alligator laying across the little road that they were riding. So they're stuck. Now we've got these two guys sitting in their rover waiting, and this, you know, prehistoric reptile is laying across the road. And so they waited, and the guy hauls up in a truck, you know, and he grabs a thing and lassos a sucker, throw him off into the water on the side, and then they go on down to business. We had an LLTV. We actually had 4 LLTVs, Lunar Landing Training Vehicle. Okay, this was a pretty good ship, but the problem was, of course, everybody was scared to death of flying it. Now there's only one left. It's in the Teague Auditorium. Okay, tied to the ceiling. What it had is a regular jet engine in here that fired downward and supported 5/6 of the weight of this thing. Okay, and then it had 2 500-pound engines that controlled the thrust, so you could control up and down so they could practice going down. It shake, rattle, and roll really, really bad. It was always the thing. There was a attitude control system that was good but not great, and we were lucky it never hurt anybody in this thing. Okay, we crashed 3 of those. Neil, since this year, you probably saw some of the movies of Neil Armstrong getting out of one of them, okay, because this control system went out of control, and he had to wait and eject out of it. Joe Allegrani, we lost him this year, but he was out of one, and I think Stu President was another one. Anyway, there was Bud Ream did the 3rd one. All of them got out on time. It was a bad deal. It was the best thing we could come up with at the time, and then later they said, well, the simulator's better, the digital simulator. We go back there because you might get sweaty in it, but it's not going to kill you. But this is how it looked like underway. In the Building 5, remember I talked about the big translation simulator. Now, Mercury's been taken down, and you were rendezvousing with the command module and LAMP. And we had this stuff so you could be active. You could be one or the other. We'd have to go through a swap of who was be the active. The one over here is the active one, so the astronauts were in here looking at rendezvous. And the trick was that because of gravity, you'd have to pitch over and lay on your stomach to actually go through the rendezvous, the docking phase. Right? What did we learn? Interesting thing. Guides and navigation between the planets, cislunar navigation is called, was understood, and it turns out it was operationally pretty easy. As long as you could find the stars, as long as you knew the stars, or your automatic system in the future could find them, you could do the navigation. And that's a different lecture sometime you can come here. Landing was straightforward with the manual controls that we had available. Okay. Lunar surface EVA was okay. It was not great, it was okay. They had problems sometimes with overheating because the sun was so vicious. We could do okay when you're outside the spacecraft in orbit because you just got the sun. When we were on the moon, we found out we had the sun, and then we had the reflection, just like you're on the beach. Okay, and the albedo of the moon was so high that they got double sun, kind of thing. Okay. The EVA gloves were a problem, and they continue with us today. It's always the worst problem we have. So we think we could go back to the moon, land anywhere within our capabilities, and we thought at that time we could go anywhere else. That was just how we felt. And I talk about that for a moment. This is what the vehicles we built for Apollo. Little Joe was purely to test the emergency system, and we're about to do a series of tests like that now at White Sands. We built 10 S1s, then we built 10 S1Bs, and then we built 15 Saturn Vs. Okay? We used 12 of those for the flights. We never used 13, 14, 15 Apollo. This is a picture inside Michoud, Louisiana. At that time, when they're building 1Bs, we were going to build more 1Bs. We were going to build more Saturn Vs. There was another order for 10 more Saturn Vs ready to go in when Congress told us that we're not even going to do it in Apollo 19 and 20. And later, they even took away 18. Okay? It never occurred to us that anybody would stop. Now, does that sound familiar? Like right now, you know, there's somebody shut down the shuttle, which is a crime against nature. This is what a 1B looked like. And I want to go back a second. These things maybe you didn't notice. Remember Al Shepard's flight? He rode a 1B. I mean, rode a Redstone. These are Redstones. Okay? You put a bunch of them together, and the center of this thing is a Thor rocket. We didn't ever ride one of those until we get it in. That's how they built it. They just took existing hardware. They had the tooling to make these cylinders and all that stuff. You just strapped them all together. You see that the thing that's holding it all together is these two rings down there, and that's a Thor in the middle of it. It's fatter. It's an intermediate range ballistic missile. And there you go. That's Michoud at the time. We had a fleet of barges ready to take them down the Cape. Keep going. Okay, this is the Michoud is where we build the external tanks. Used to build the external tanks. I think the last one has just been finished. Well, now we had some hardware left over. So Skylab came along. Skylab's a good name. Originally it was called Apollo Applications. Some smart guy said, we got all this hardware laying around, what can we do with it? Okay. So we came through to prove that people could live and work in space for extended periods of time, expand our knowledge of solar astronomy and a bunch of Earth-based observations. We did about 300 scientific and technical experiments, medical experiments. It was a major medical experiments thing. It was that by itself is awesome, a lot of detail. And then Earth resources. We did a lot of high multispectral photography of the Earth for the first time. It was built inside a laboratory. We took the S4B is the tag for the third stage of that setting, and number 513, we used it. We flew 3 crews. There was 4 weeks, 8 weeks, and 12 weeks. The second crew stayed up 3 extra days. They did a tremendous amount of stuff, and science was now getting into the thing. For the first time, you didn't have to, you know, have a bowel movement in the middle of the conference room with everybody else hanging around. It's kind of a step forward. We're going back, of course, now. This is what it looked like. They put in floors. The floors were open floors so that there was still ventilation going on. We lived in the hydrogen tank, and this was, I'm sorry, we lived in the oxygen tank. Good, right? This is the hydrogen tank that we lived in one of the tanks. It's the other way around. Yeah. I said it right the first time. The inside, they just hung, it was going to be zero gravity. So there was almost, I won't say no rhyme and reason, but you just hung things on the wall where they fit. Okay. So this is Pete Conrad working on a furnace, so you could do all kinds of flammability experiments. Oh, going the wrong way here. Thank you. This is another view looking down the length of this thing. And this is in now Building 5. We got some paint, painted it white. Okay, this is that south side. And this is part of the vehicle that would attach, this thing was inside there. Okay, and the gravitational was such that we had it on wheels. So we'd actually roll it around to get gravitationally accessible the thing that we're going to work on today. We just turn it around. Okay. So we did all that stuff. And then this is an airlock simulator because we went outside to recapture film and things going on. This is one of the crews. The other thing we proved is you didn't have a simulator that exactly looked like a vehicle. We talked about part task training, okay, and we proved that that could work. This is nothing but a little shack in Building 5, another part of it, where all of the digital electronic stuff worked, and the Skylab simulator, they called it, they would sit there, and in this case, Jerry Carr is working on the solar telescope. Over here is one of the guys who's keeping his electric power system and everything working. Okay, so they would sit here, and there's nothing like the vehicle at the time, but the training was just good, and it transferred immediately into the world. This was a little conference around the wardroom table. This is the place where they ate their meals. This is inside the mock-up. By the way, you can go and see this one. This is the one that's at Space Center Houston. Okay, when Space Center Houston was built, this thing is so big, they took it out of Building 5, put it over there, and then built the building around it. Okay, there's no door in that place that's big enough to put it in. That actually building is sitting in there. We had experiments that looked through the window. We had airlocks here that would look, fault lines here, putting stuff outside. This is more of the stuff looking at the solar. We had simulations of solar flares and all kinds of things like that. This is what the thing looked like. Remember the Saturn? Here's your first stage and second stage, whereas the third stage is here, but this is now the Skylab. And then up in here is that telescope. So it's once it gets in orbit, you lose the shroud and then you tilt it down 90 degrees. This is what it would look like without the command module. This thing would turn down, and you had solar arrays outside of this one, and then 4 that would come out of this solar telescope, and you'd be up and running. First time we really used photovoltaic. Now, the 1B, we had saved a lot of money because somebody said if we built this tower, then we could use all the upper part of these access arms, just like the other Saturn did, but we just didn't have the other pieces down here, so those were taken away. So this milk stool we used for 3 flights, for Skylab flights. When we get up there, though, we found out there was a problem. We launched this thing. 2 weeks later, we were going to launch the guys to it the next day. On the way up and going through max dynamic pressure, the worst time going up, going to orbit, max Q, it tore off one of the solar wings, because what happened is the wind had got underneath this micrometeoroid shield that was all the way around here. It was a black layer that was around here that was supposed to come out about 3 inches away from the inner wall. Anyway, it was badly designed. It failed. When it ripped off, it tore off one of the solar arrays, and then this one over here is stuck. You can see the array is on there, but there's pieces of debris holding it down. So the crew in 2 weeks trained how to go out and do an EVA and fix this. Now, one of the funny stories about this is when they came in and they docked up here on this side for the command module, the upper part of this thing was okay. It was cool in here, but down here was about 140 degrees because the sun shield that was supposed to be there is gone. So the pure, intense solar radiation is put it in. So the air temperature is 135 to 150 degrees. It would go down at night in the shade, but it never got any far down before the sun came back, 45 minutes later or so. And the funny thing is that Pete Conrad, who is a Navy officer and always had something to say, talked about the fact it's a good thing we're talking movies of this one, because when they went down, they were using work gloves and tennis shoes and damn near nothing else, because it was too hot to wear anything except maybe a pair of skivvies, and that was it. And they managed to do the job. They put out an umbrella through one of the airlocks on the sun side, and then later, this is after the second flight, they put up even a better sun shield, and the temperature got down to about 80 degrees, and we lived through this thing the rest of the time. What did we learn? Okay, first of all, a new word, space adaptation syndrome. When we flew Mercury, Gemini, even in Apollo, you had a very small space to work. Okay? And so what you got into is that people didn't get sick because everything felt like the simulator. It felt like everything was normal. This thing was huge. I mean, it was, the volume of the thing is something similar to this, okay? A big, big area. And so you could be tumbling around in here and having a great time. The problem was there was a collision. Now we know there's a collision between your inner ear, which is just happy, thinks everything upside is right side up, but your eyes are showing that you're clearly upside down relative to other people or other things. So there's still not a total understanding of what's going on, but this is part of our problem. So we want to fix this thing. There's a lot of things we need to do. Maintenance and repair is possible and should be planned. Train crews in a simulator didn't have to look exactly like. Realize that only time-critical events need to be repetitively trained. You know, you have to get things, some things, but you don't have to have just everything. So there was a more relaxed training in some areas. And the timelines with the flight plan where the people follow, it's the same way. Some things are critical, other things get put in like a job jar and just get to it when you can. Those are those lessons that we've learned a couple times over, we got pretty good at it. Okay, then, now, in 1975, a détente, back in 1973, kind of a détente is like a cooling off for the hot war that was going on. You know, it was the Cold War, but sometimes it get hotter and then it cooled off. And there was a chance for Nixon, President Nixon and President Brezhnev at the time to sign a protocol that said we would plan and fly a joint mission to prove that we could rescue one of our ships if somebody gets in trouble. It was in July '75. And the big thing that showed up is that an androgynous docking system would be important. An androgen, in this case, there's no male and female. When they both have male and female components, and you can, you know, either one can be active. Okay? This is what it looked like. This was our last Apollo service, command service module. Okay? Last piece. This thing is the docking module that we put in the middle of it, and this is that docking thing. And here's the Soyuz had another one of those. We put it together. The reason this is called a docking module is for that, but actually it was an airlock, because the Soyuz ran at 15 psi, where the Apollo ran at 5 psi. So we actually had to go through a lock to change the pressure when you did it back and forth. But we did it successfully. This is what the crew, in this case, Vance Brand, Tom Stafford is the commander, and Deke Slate finally getting to fly. And the Russians was Alexei Leonov and Komarov, I can't remember his first name. Anyway, these guys went in there. Here's the androgynous system. This back in the simulator, command module simulator. That's the only one left. The LEM simulator by then has gone away. And this is one of the early simulators for the Soyuz over in Russia. They trained in both countries, did a lot of good. They had a lot of interesting times. It was kind of a curious thing. When they went back and forth, it was interesting because the culture changed and the philosophies of training and everything had changed too, and it was very interesting. When one time they came to, well, remember back in Apollo 13, we had problems. You had to go in quarantine before you flew. Well, the Russians didn't have that problem, but they started doing the same thing. So they know a good deal. So they built a building where the crew would live before they flew on their flights, and the name of the building is the Prophylactorium, which is, of course, when you think about it, it's pretty good. It prevents sickness and all this sort of thing. It was just a nice little inn with nice hotel rooms and everything like that. It's a great place. We still use it today. It's called a Prophy. Nobody says this whole thing anymore. But anyway, the fact is that it was interesting. This is the Cold War still, even though we're working together. Some of the things we learned, like there were KGB agents that would come over to the United States with the scientists. We had to work with all these people. And one of our big tricks is to figure out which one was the KGB? Because they never contributed anything useful, right? And, you know, so we'd have to compare notes in the meetings, you know. But when we got to, in this crew, because of the nature of the beast, there was a prime crew, we had and then a backup crew and a support crew. We actually had 9 people in this training process. We did that through most of the Apollo. And so everybody came in for a big party that was going to be held inside that prophylactorium. And of course the Russians were living there at Star, this is all at Star City. And so the crews are coming in now from the airport and everything like that. And Bobako, one of the astronauts, comes up here, and his wife is with him. I mean, it's a big deal, so the wives came together. And so they go in, here's this brand new building, and they open up they start unpacking their suitcases, and open up the closet, and there's no hangers. What are you going to do with all this stuff, you know? So they did best they could, got dressed, and went down to the reception that's down on the first floor. Okay, and he's talking to another one, Bob Overmine. He said, how's your bed and everything? He said, oh, it's great. He says, but we didn't have any hangers. And Bob said, well, you know, tell your room. He said, back up. So we're back up there. He says, boy, what we really need is some hangers in here. That's what we need. You know. Then he left, went downstairs, waited about 10 minutes, came back up. There's all these hangers. That was pretty good. Really cool. So they went down. Of course, they're, you know, the suds are flying. Everybody's going along, and now they come along, and Deke Slayton, who's the prime crew, comes along, and they had somehow tell him about talk to your room, you know, when you need anything. and Deke says, really? I mean, he's great. You have to realize what kind of guy he was. He says, really? Come on. He said, come on upstairs. So they immediately ran up to Bo's room, and they opened the door, and he's talking to the 3 guys now, you know, and suds and everything. He says, how is it? It's really good. These people are treating us so good around here. Deke is talking. He says, but it's so deadly dull around here. We really need like a pool table or something so we can do something at night. Downstairs, back to the party. 3 days later, here comes this big moving. Only 3 years ago, this old shabby-looking, nasty pool table, they slid it out of there and put a new one in place up there. It's been sitting there ever since. Old simulator console. Now this is a simulator that's a last gasp because this is the last Apollo spacecraft. This is in Building 5 where you have mock-ups. We were getting into the mock-up phase where we're learning how to do the training and go through the procedures. And you can see that things with multilingual, all this kind of stuff we're doing. But time came. This is the Soyuz launch successfully. As soon as it got to orbit, 3 hours later, we launched on the 1B. Rendezvous, found it. There's a picture of the Apollo looking the other way. This is actually, it's not snipped out, but there's a white cloud bank down there. I think that's why the picture looks like that. What did we learn? Space rescue is really real. Training with 2 language, 2 training philosophies, 2 sets of training hardware is difficult, and time expands. Okay. And of course we learned out. The STS. Everybody knows the STS. We all call it the shuttle, but its real name is the Space Transportation System. We're going to create a reusable spacecraft. We haven't done that before. Every time it's a one-time deal. We're going to move cargo from the Earth into orbit cheaper, more reliably, increase the creature comforts, and then create the infrastructure, build a station, and then go out again. We're working again. Okay? This one was fancy. We got 5 digital computers. 4 are formed a primary set, and a single one does a backup with different software. It's fly-by-wire, 3 fuel cells, really good environmental control systems, best flown up to them. Hydraulics, because you had to control all the things, like rudders, elevons, and everything like that. And it had very, very advanced main engines, and then heat resistance tile. These are the 2 big things that we get along the way. This is the main office of this operation. This is, of course, with the latest one, you should see. But there's a 2-story spacecraft. It's got a flight deck where the guys, there's 4 people riding here, and then 3 are launched down in the bottom. You can carry up to 7. We have carried 8 once, but everybody agreed that was too many. 7 is all it was. We were ready in the early days. We were going to not launch just from Kennedy, we're going to launch from Vandenberg. We're going to have a set of blue shuttles. That is, we're going to have Air Force, their own vehicles. Okay? I don't know what color they were going to paint them, but they call them blue shuttles because I just meant that. But in that case, you would go polar orbit. It was going to be able to fly over Russia and everything multiple times a day instead of the few things we would do. Now, I don't want to get into the details of this, but you didn't just launch and go to orbit, but on the shuttle you had lots of abort modes, okay, where you had to fly back to the Cape, or you would abort going across into once around and then land in California. And then after we got through that for a while, we got another one where you wound up, if things were really bad, but you could make it out. If you don't get all the way to orbit, you could land in either Africa or in Spain or in France, somewhere where you'd loft over and then you'd keep the vehicle and get it back. But it's because of engines that would go out, certain problems on the way uphill. Now the training expanded to so many different things. Because it's an airplane, because it has different ways to launch, vertically, land, horizontally, you've got all the kind of things. So how to get out, okay? You'd have a slide, you'd go out this way. You would do other kind of things and you'd escape different ways. This crew is just getting ready to go. These are orange suits, are exposure suits, okay? Most of the Earth has got cold water in it when you're flying over these things. And so this would only last a certain amount of time, but isn't that interesting? Those look like the old ones. It's very, very orange. You've seen them. I don't know what. Must be the projectors giving you a very different color. But you get the idea. They would last several hours in the water. But the fact is, we go through the training. If you land on the ground horizontally, you have to. You can't get through the bottom because of fire or leaks. You actually rappel down the side. You can bail out. You have a pole where you bail out through the side, and then your parachute opens up. You land into the water, and then you expose the little raft that you have. Okay, you have a Mae West that's built into that suit, and you go through all that sort of thing. You can see the depth of the thing. Now EVA training, which we kind of soft pedaled around here, that was kind of out of focus. But you get the idea that the MBL training, which is back here on Space Center Boulevard, gives you an enormous amount of space. It's 100 feet by 200 feet, 40 feet deep. So you give you an enormous amount of area to work in. And even so, with Space Station, isn't big enough. But you can see the tremendous amount of stuff we do. The EVA training has developed into a fait accompli. I mean, it just works so well. And now we just work, everybody that's in the water, there's a safety diver, 2 safety divers for each astronaut in the water. There's camera divers, utility divers. It's just a ballet that goes on. When you're coming home, the shuttle has big engines getting into orbit, then the engines are never used again. And so when you come down after you deorbit, instead of rushing through the atmosphere just like a blunt object, you come in under control, you fly with a system where from 4,000 miles away, you fly dead stick from 150 miles up to about 50,000 feet, about 10 miles up. Okay? And when you do this all right, you right over the runway. Okay, that's what your goal is, to come in so you have 50,000 feet right over the runway, and then you change to what's called TAME, Terminal Area Energy Management. You did an energy management all done down that says, here's my potential energy and here's my kinetic energy, add all that together and look at the range and make sure I've got enough range to get there. Once you've gotten there, now you do this kind of thing where you spiral down out of the sky, doing it what a pilot would call an overhead approach. Okay, and the way this works, if you could think this circle, instead of think of it as a cylinder sticking up, like you're flying down the outside of a soup can. So you come in as you hit the tangent of it and you fly around the radius of that thing, and then you come off into the final. Okay, that works. You see them all the time. Generally, you always see them suddenly 50,000 feet or something, and they're always doing this long, slow turn coming around. What you're doing is controlling, giving away the last amount of your energy because you're gliding. Remember, you can't edge any power. It's not like Southwest Airlines, when if you don't do a good job, you missed approach, you just add power and go around and do it again. You're going to land somewhere. So you're going to make sure it's the thing with the numbers on it. Okay, this is the simulator. Interesting kind of stuff. This is John Young and Bob Crippen. We're getting ready. And partly in the simulator, this is one thing. One of the things you can't do is take coffee in the simulator. And one day, this gentleman here had a coffee cup sitting right there, his Hoff brew, and John didn't know this, of course, so he turns around quickly, spill the coffee down through this panel. And of course, you don't know that because he didn't intentionally see it yet happening. But the simulator does funny things when you throw coffee down some of the, just everything went down, zero. So we had a lot of talk with that. The simulator itself was an interesting thing. You can see Brian Duffy here working, but the crew is working together. They're learning their procedures. They're making the procedures better. They're doing things like that. Okay. So that simulator is like their office. It's a continuous improvement process as you get going. And here again, this is Eileen Collins, same kind of deal, where they're working through procedures, change them, make it better from what they're doing, and so on. We fly. Of course, we've flown almost 130 times. I'm not going to go through the millions of flights we've done, and then finally come back down. What did we learn over that time period? Basically, over 30 years we've been training, because the simulator started in 1977. Okay? Complex vehicles like this are, and the complex experiments we fly, increase the training time. We have long periods of time. If you have a slip or something like that, it just drives the cost up, because the meter runs. That is, you got to keep training. You can't stop training because then you lose the skill base. But the problem is it causes trouble with the controller, with the families, just as well as with the crew. So delays are a bad thing. Anyway, we roared right into the middle of this thing a couple of years ago, 1994 or so. We got another thing to launch with the Russians. Rendezvous and dock with the thing, start an interchange of medical things. We even took one of their modules called Spectre and outfitted with a bunch of American things. Mir was a strange looking beast. I mean, it had these, because it was made of different pieces like this, it looked like a dragonfly or something like that flying around in orbit. But we docked to it 9 times, transferred a lot of thing in there, took our people in, and did a marvelous job of learning how to work with the Russians in a real true sense. What did we learn? First of all, training in 2 countries and 2 languages is just as bad as it was in ASTP. In fact, it's worse because the more complicated systems raise the total time. Procedures in 2 languages. A body of medical data was obtained, still being analyzed, but the fact is it was a tough job to get. But the big thing that we learned, the worst thing maybe, is that stowage is a big thing. Mir, Bonnie Dunbar said, when you go to Mir, it's like spelunking. Here's these big things, but so much stuff has come, and it just filled it up. It's like one of these people you read in the paper where their whole house is full of newspapers and stuff. They never threw anything away. Stuff goes in the house. That's what Mir was like. It was just full of used equipment and other things, and there was no ready to throw it away and get rid of it. So it gradually got thing. The stowage was bad enough that critical items could be lost or used up or discarded. Sometimes we even just didn't know where they went. So that was a major, major problem. Well, now we come into the International Space Station. Now we're going to create a permanent outpost, okay? And it's a national laboratory. It's kind of like Los Alamos or one of those, to provide all that uses vacuum and other conditions. The thing is we're going to provide a testing ground for space technologies we think need before we go back up in the solar system. Well, the trick is here, it's all of those things we talked about, but worse. The training presents at different things. You've got 16 nations and 11 language. You've got 41 shuttle flights planned, 12, most of them are done now, 12 Russian assembly flights we used, and then we used Soyuz in progress also to ferry people up. There's 6 control centers, 7 training sites around the world. Okay. When we started out, if you added up all the things you had to do to be ready to go to a space station, it was 4.5 years of training. That's as much as you get to do in another degree. We cut it down and cut it down, went to 2.5 years, and now it's down nearly 18 months, but it still hovers around 2 years. Okay. Complexity from the Russian involvement to us meant we had to learn another set of equipment. We had to learn another language. So did they, of course. Laboratories on the ISS increased from 3 to 5. Totally, it's almost like 2 total different vehicles are joined together. That's what the space station is like. It's flying along. Okay. Time of travel and the cost between the 2 places is is enormous. But we did it. And it's interesting as it was built and built and built. Of course, we lost a couple of years because of Columbia, but when we got to this point, the training, this is one of the modules, training in Russia. And of course, we finally had the on-orbit kinds of things going on. The clay and the control post of the station. Nicole, just as a new one, just because I want to bring up to today, this is Nicole Stop. She's walking on Colbert, right? This is the new treadmill thing. But the size of it is what I want to do. This is a little training thing we do. You can imagine the size of this thing. How many of you saw the movie 2001, Space Odyssey? Remember that? Yes, had an impact. Do you remember the spaceship that they had? This enormous thing, because they'd see it coming by, floating out there. The fact is that this trust that we built on the space station is about the size of that spacecraft. He said it was 425 feet in the book. Okay. This is 330 feet. This is an interesting thing we did. This is one of my people at Titronics. It's sunrise coming up. This young lady is coming out of the hatch, swinging her legs out just as sunrise arrives, coming out of the Quest thing. Camera pulls back. What you do? Get an idea of the size. This is how it looks today. Built that. It's up there flying. And I'm proud of us. Really. You know? So now what are we learning? Let's go another way. Multinational programs, awesome implications, go on like that. Training in multi-languages, storage. ISS is as bad as the Mir ever was. Okay? We don't know where anything is. We always have to have two of everything before we lost the second one too. You know? We have to work to design programs where family life is in mind. Okay? People can't get into these things either on the ground or in orbit because the long separations, the training period before you fly amplifies the problems you get into when you do fly. And if you're talking about going to Mars or somewhere else in the future, it's going to be just that much more. Let's give you an idea. Summary. We're almost done here. Mercury, we trained everybody about 200 hours before flight. Skylab is a lot. Shuttle is way beyond 1,000 a lot of times. Certainly if it slips or something happens. ISS is up here, and remember this is only a year and a half, and we had 4.5 years when we started thinking about it. What the heck is this one? You know? Sometimes I expect that what we should do is have a degree in aerospace operations. So you learn how to do a lot of these things and get your degree that way. It's our challenge. Systems to leave the Earth are adequate. Human systems are inadequate. We could leave, everybody says, let's just go to Mars. And systems-wise, we could do that. We could do that. Human system, I don't think we're ready to do that. Here's the size chart, if you would, between the old Apollo, then the shuttle, and then the two new ones. We can do launch. We can do abort training. We can do rendezvous and docking. We can even get home. But how do we control the hours? Start earlier, maybe at university, okay? Use just-in-time training, okay? This means you learn as little as possible before you go. Just the critical stuff, and then you train the rest of it when you're there. Okay? Design with control harmony. You know what control harmony is? You have a car. Yeah. Have you ever rented a car in Des Moines? You get in that car and you just drive away because the vehicle has got control harmony. Okay? It'd be a lot easier if every space vehicle we go forward, it's not just the stick, but it's the controls for the environmental control and for the propulsion system, everything like that. It's the same controls. I mean, what do? You're going to turn the engine on or turn it off. You're going to make it cold in here or hot. Make it always the same. So if you learn to do one, you can be certified to do the other ones. Save a ton of money, save a ton of time. Designed for repair, and designed to do something with the stowage problems. We need to challenge the children out there, our children, everybody's children, keep them in school, instill the desire, and we just need to go further. Maybe there. Call that the Columbia Moon. I don't know if you know, that was taken by the Columbia crew before they came home. They set it down electronically. Thank you. Any questions?
We'd like to thank the University of Houston Clear Lake for the building, the aiaa-Houston for helping out with volunteers, and the Ad Astra Rocket Company for filming and pictures. We should have some time for questions.
Sounds good. Anybody? Yeah. Right.
On the subject of cross-cultural conflict and problems, are there any overall differences in the Russian philosophy of training that in contrast to our own? How would you compare the two approaches to training?
Let me tell you about it. I'm trying to get back to something here. I can make it happen. All right. Russia is an interesting mix of philosophies because in America we tend to open the big picture and then teach you the details. Okay, you have to open the big picture. If you go to Japan or China, they start at all the details, and then they build up the big picture. Okay, when we take our astronauts there, it drives them crazy because you got all these details, but you don't know how to plug it all together. Okay, Russia, it's funny because it's got the two cultures kind of blended together. So some things they do the big picture, the details. Sometimes they'll do details to the pictures. So it always kept us off balance for a long time. Now we know a lot more about each other, and we've kind of settled down that their astronauts are kind of like our astronauts. That is, they're all jet pilots. They're all the kind of people. They want to know where's the stick and how did he normally fly, and then dig down. So we've kind of gravitated to that kind of situation. It's interesting to think about that. When we first got to them, when we got to Star City the first time, there was one copying machine in the entire place. And you had to make a reservation to use it. I mean, not us. That was them. You know, we didn't get close to it. Everything that we did, the simulators never had names. There was no Gemini mission simulator. There was no shuttle simulator. It was an MK342. Okay, and the reason is that it was a code name so spies would not know what the hell they were talking about when they intercepted messages. It was all still built like that, you know. It was very strange. We didn't know what the hell the MK342 was doing. And then finally walked by, and here's this thing on a chart. I was in somebody's room one day. Well, that's the simulator. You know, and finally could see my pidgin Russian was enough to figure out what the heck this thing said.
What about the number of hours of training per day or per week? What have we learned over years of working with people about what's better? I mean, like 12-hour days or 8-hour days or 4 hours with fun? Or?
What we found is that it runs something like 20 to 26 hours a week of real training on average. Okay, and that means you may go do an 8-hour sim today. You do a 4-hour sim tomorrow, and then the afternoon you do another one on Wednesday. Things like that. But along the way, what you get into is you also got a suit fitting in the afternoon. You know, I mean, we have people that tailor those blue suits and even the spacesuit. I mean, you don't want your astronauts to look bad. Right? It's even better because when you put orbit, you get 3 inches taller or so. So you don't want the waistband, and you don't want the belly hanging out. So we have to get suit fit. We have things like that, other than the heavy-duty, mind-blowing kind of simulations or training. When you start out as a new person, you go pretty much 20 hours of classroom stuff a week, okay? And then you study. for the other half of that time, because you don't have much else to do, you're rolling. That would be. I think when you get to the point where you're a flight crew, a prime flight, one that's about to fly, it ramps up. Okay. I think there's a pucker factor that's involved there, because you're going to be the one that's on the spot to do good. It's like Al Shepard's prayer. It says, "Please God, don't let me screw up." That's it. In public on TV. So, just before you launch, the guys almost always we launch people that are exhausted. They're so damn tired. And it almost came from them. They want to do more. They want to get one more lesson, one more session. And they'll come in with the instructors, but they'll go through this stuff and say, "Could you guys meet me after work? I'd just like to go over this checklist one more time, a couple hours, from 5 to 7, something like that." And then when they go into quarantine, when you can't see their kids anymore and all that stuff, then it goes up even more. So the last 7 days they're there. They're really busy. Some of them are much more relaxed. They've been there before or something. But the new guys are always just going crazy. Okay. Then you have the other side of it. There's the physical training, because they want to go out there. They want to be in good shape, especially if you're going to do EVA, if you're going to be in a spacesuit. I don't know if you know, we mentioned, but the gloves are a big, big problem, okay? Anybody in here work on EVA or know the suits? Anyway, the fact is that a spacesuit is like a big balloon. So if you put yourself in a balloon, your gloves go, okay, they're just, because the air pressure it's a vacuum outside, so it assumes the glove shape. So to pick up a hammer or whatever else, it means you've got to have enormous strength in your forearm to just make a fist. And in fact, most people, you can't make a fist. That's why if you ever see the hammer that we use, actually carry a hammer, the handle's about 2.5 inches in diameter. So you can hold it like this. Okay, so you don't have to come down the size of your Craftsman hammer that you have at home. Okay. So they walk around with tennis balls or those other squeeze things, because they're doing all this building up the forearms. So you're talking about some thing over here, but that was giving it this action. And the women were even worse. I mean, because we had some women and really working hard because they're coming from behind. They didn't build up that much before, so they had to work harder at it.
You read my mind. I was just going to ask you with STS and ISS, have you noticed any gender differences in training between male and female astronauts?
None that I could talk about. No. The biggest change that happened in 1978, of course, is we have women join the program for the first time, okay? And it had a lot of great things. We had 6 great ladies come in, okay? And it set off a whole chain of reactions of all kinds of things, It's a good old boys' party, and suddenly here are these people coming in. And it was the same thing was happening on my side, because I had started hiring a lot of young women engineers to become instructors. Okay, so it's going through all this stuff. The astronauts who came in, Kathy Sullivan did an EVA. Kathy Thornton did EVA. I think you had to be named Kathy before you could get to do it later. But Kathy Sullivan was a bigger woman, big bone they call it. She was not fat, but she was bigger. And so she did pretty good. But even she had come through the problem, after making it. The one thing that happened, Kathy Thornton was small. And she was the last one we did that was like a petite spacesuit. We did, just for cost. We had small, medium, large, this kind of thing. And then we just threw away the small because it's just too expensive to keep all these different sized up, okay? So if you fit in them, it turned out to be big and bigger is what we settled on the spacesuits. And if you fit on one of those, they could be qualified to go, okay? But it was people are so funny. When you take women into space, if you take people into space, you get a fluid shift. You understand what's going on? I'm standing here in gravity, the laziest one in the room, okay, has incredibly strong thigh muscles, because at least you can stand up in this gravity field and walk to dinner, right? Okay, so when you get to orbit, the first, we could have had a contest to see who was the most lazy, but you get the idea. When you get to orbit, the first time you flex those muscles, okay, when you flex them now, actually, let me go back a notch. Your heart is pumping blood to your body. Wrong. The blood is pumping pumping blood to your head, okay? In the aorta, it just pumps it out over the hill and, you know, it goes down by gravity, okay? And your thigh muscles and everything are pumping the blood back up, okay? Every artery, they're little one-way valves. They're opening all the time. Every time you do any kind of thing, it shoves blood back uphill, and those little valves close to help hold it there. That's why it's so painful. People who have varicose veins, because it's a malady of those little valves. They leak, and the blood pools down in your legs and breaks the vessels down and all that sort of thing. Okay. Well, now, when you get there, the first time in orbit, you flex your legs just to get out of the seat, and all the blood rushes back up to your torso, upper torso, and it doesn't go back. There's no reason for it to go back down because there's no gravity. So if you ever know an astronaut friend, and then you see him in orbit, it looks like he's on steroids. Okay. All this fluid shift goes on. Okay. Well, then it just stays there. And the problem is there's a sensor at the base of your brain that decides how much blood you need. Okay. And of course, let's say I'm buried in blood here. I got too much. And so immediately you have to go to the bathroom. You got to pee. Everybody got it at the same time. This is a one-holer spacecraft. 7 people. So it means that you got to take numbers right away, right? And over the next 2 days, you will lose 30% of your blood volume. Okay. You will urinate away that much. Okay. And then you get to a stasis. Then you're okay because it smooths out and everything's good. In fact, you look at them, they don't look as bad after about 3 days. They're still a little bit puffy, but not bad. Inside your body, what's going on is you shut down red cell and white cell production also because you have too many of them. And now you have too much because it's thick, because 30% of the plasma's gone, but all the cells are still packed around in there. But when they die, they're just gone, and you don't make any new ones until about 28 days out. Then it starts picking back up, and you start making new ones. Okay. Well, that's all cool. That's a stasis. You can live with that. If you can keep your muscles going, that's a whole separate story, okay, about muscle degradation, because it's so easy to be there. But let's just stay with the blood. Now, the mission's over and you want to go home, okay? So you fly down, it's really good. The pilots, we know, we put on a G-suit. It's like a pair of pants that has air bladders built into it, because up in the front seat, when you start making those turns, remember all that turn that the shuttle's going to do, all that lack of blood, you're 30% down, it's like you donated 2 pints. So blood's going to leave your head and you're going to pass out. So the G-suit is to shove the blood back out of your legs up into your upper torso. But that's only the front seat guys. And once you get home, then, I mean, you drink fluid, and it just disappears. You don't have to go at all. Your body just goes, just needs it, okay, comes back up. If you've been there 28 days or so, you're anemic. You're down. You need to make more red cells, white cells, and things like that. So that somebody coming back for 6 to 8 months or a year in orbit has got some things to remedy. They also have to do some things with that. Now, what we've learned a lot of times is we drink a lot of fluids before we come down. It's electrolyte fluids, kind of like Gatorade, but of course it's our own NASA brand. But we go through this thing, and when you're ready to deorbit, everybody's in their chairs, pretty much everything ready, and you say, okay, 10 minutes, 15 minutes out, about a gallon. You drink all this stuff, because then it's going to hydrate you as you're coming down, okay? So that when you get down, you're not going to, all of those guys in early flights, this all happened to all those early guys, but nobody knew what was going on. They'd come up out of their Mercury spacecraft or their Gemini, you know, and they'd get out of the spacecraft off the helicopter, tow her across the flight deck and down the seat back. They laid them down and they said, you're great, 100%. The guy stand up and he'd pass out. They know about this fluid thing going on. See? So, well, now we hydrate them, so we don't want any, you know, it's bad on TV to have you guys slumping down. But the fact is, okay, you put your gallon down here, everybody's good, and then they say, we're waving you off because of weather. Remember, it's a one-hole spacecraft. Guess what? We're back to the numbers. Everybody's got to, you know, because now you're going to have the same problem. Taking people to orbit is an interesting thing. Human animal is fascinating. Okay, I've spent my whole career with it. I mean, today when you decide to come here, I hope you brush your teeth, you know, combed your hair and everything, or you wash, you know, you comb your hair, you look in the sink. What's in the sink? Hair, right? Now, if you did this when you're in orbit, Where's the hair? Right? You don't want to fly with anybody with dandruff. It's interesting to see the, the light beams coming in through the sun. We had a couple of experiments where we took animal cages, and they were well built, okay? And the thing is, it was always built so the ventilation was such that it sucked the air in from outside and went through the filters to keep the fecal matter in. But they failed on one flight. And Bob Overmeyer was the commander, and he said, it's rat shit, actually, is what it was, okay? And it's all over the Skylab module, okay? And so you had to wear masks, and the problem is then you go out front, we'd only eat up in the front, when you go there, but pretty soon they're migrating, because if you go through, then you're carrying a few in the draft, and he says they're down on the mid deck pretty soon. It's like the aliens are attacking, And he says if those suckers get on the flight deck, we're going home, But it's really bad. It's a good thing that we didn't have any Raisin Bran, to eat because. Any other questions? Yeah.
Can you? Yeah. What is the difference in training between the guest tourists or space tourists that go up with Russians or the commercial companies that are advertising space tourism? What are the training implications from your perspective?
That's a good question. You know that the Russians have decided to sell seats for the space station, and we haven't. Okay, we took a lot of guests up there with us. When we did it on the shuttle, and the way it worked out, they only had to do 250 hours of training. Okay, 250 hours of training. And the training was basically how to eat, sleep, go to the bathroom, okay, and how to get the hell out of the way if anything goes wrong. Where's a neutral corner, just be there, okay. The Russians sold these deals for 20 and now up to 30 million, okay. They make them go through all the training because they want to make sure they get their money's worth. Okay, so that means they ride on the centrifuge, they do all the stuff in the simulator, but they're inanimate objects. They have no role. Okay, but then so they go through and they have to learn their eat, sleep, go to the bathroom routine. Okay, and then they give them time where they would go to the window and take pictures or something like that. But it's a money-making deal. Okay, so they don't spend a lot of time with them, but they'll put them in the simulator. But the big thing is they have to learn how to get in the so-called the spacesuit that they have, okay, and because that's what you use to launch and land. We train. I mean, just I can't remember, the seat line air was $150,000 or something. Just what they charge them because you get an itemized deal. But we could put somebody in orbit as a tourist for 250 or less hours, okay, and it's purely, like I say, safety training. And then how to not be a nuisance, that is how to ruin the bathroom, things like that. So you didn't have to have somebody else do it for you, which is you've all understood going to the toilet has some ramifications when you don't have gravity. So, but it is interesting because ever since you were potty trained, gravity has been a great friend. Okay?
You talked about whether the LLTV, in your opinion, was worth it, and if we were going to go to moon landing again, build a flying simulator, would just go. Because the shuttle training aircraft, I think we consider to be a pretty good, successful
Yes, it is.
flight simulator.
Yes, it is.
And the LLTV seems a little scary. So, if you were going to do it again for, say, Altair, would you recommend?
No, I would not. It's I think a digital simulator. The SDA, the good thing about it, it is a digital simulator that